and then we will discuss the further part about the theory of. Okay. All right, Aman. Okay, so I want to start with question number 2. Question 1, hopefully all of you have got, and nobody has asked me yet. So, other question 1. Okay, so let's start with question 1 instead then. Okay, so let's understand question 1 very quickly. Object experiences 4 meters per second square of acceleration when the force F0 acts on it. Okay, so if you have an object of mass m, let's say, and a force of F0 acts on it, then it experiences an acceleration of 4 meters per second square. So when the net force, this is Newton's second law of an object of fixed mass, as you know. So when this net force has a magnitude of F0, then the acceleration has a magnitude of 4 meters per second square. Okay, so that means we can say that F0 by whatever mass the body has a magnitude of 4 meters per second square. This is the first piece of information that we know. Okay. Now the question is asking what happens when the force is doubled. Okay. So if the net force is made 2 times this, okay, then the acceleration will become 2 times F0 by L. So it will become 8 meters per second square. Okay, understood, Adharv, the first part? Okay, now secondly, second part, if a second object experiences 8 meters per second square acceleration under the influence, then what is the ratio of the mass? So let's say the second object has a mass m prime, but the same force F0 is acting on it and is creating an acceleration E prime of 8 meters per second square. So you can see that F0 upon m prime is equal to 8, whereas original mass of the object was 4. So from this you can see that the ratio of the masses will such be that m prime will be equal to half of m, or m prime is to m will become 1:2. Right? So now you are applying Newton's second law on the second object which has a different mass, but under the action of the same force, its acceleration becomes 8. Okay. And if you tie the two objects together, so let's say you have this situation, m prime and m are tied together, and now you are applying this force F0. Okay. Then this whole object will have some acceleration, let's say A double prime. So F0 will become the total mass A double prime. Okay. So that acceleration will become F0 divided by m plus m prime. Now from here, substitute. Okay. So 2/3 of F0 by m, which is 2/3 of 4. So 8 by 3, or approximately 2.67 meters per second square. That will become the new acceleration. Alright, so hope this part is also clear. Yes, I'm coming to these questions, 7th, 12th, 13th, etc. Ask me. Yeah, Vineet, it is correct. I'll explain the question to you. Don't worry. Okay, let's move on to the second question for those of you who asked it. Others, I'm assuming, have got the second question correct. So now what is happening is, in the second question, now we similarly have a situation where on a mass, if you apply the force F naught, it creates an acceleration, let's say E naught. But this time that is given 5 meters per second square. So this is equation 1 which is given to us. Now the situation shown to you is that in the first case, on a frictionless surface, you have F naught and another force of magnitude F naught, but acting perpendicularly like this. Okay. So the net force here will be, suppose, so in a proper equation, you can show this as some force F1 and this is some force F2, where magnitude of F1 is equal to magnitude of F2 is equal to this original force's magnitude, but the angle between them is 90 degrees. So the net force will become the vector sum of F1 plus F2, because this is lying on that frictionless surface, as you can see. So weight and normal reaction are balancing each other, but along the surface, along that horizontal surface on which it is lying, this is the force. Okay, so the vector sum of these two will be a force in this sort of direction. This will be the net force, and the acceleration therefore of the object will be along this direction. It will be along the direction of the net force. So acceleration will become net force divided by mass. So this will become such that the net force has a magnitude of square root of F naught square plus F naught square. Okay. So magnitude of this becoming this. So substitute this over here. So root 2 times F naught by M. So that becomes your second equation. And then substitute this here. So F naught by M is given to us as 5. So the acceleration in this case becomes 5 root 2. Approximately 7 meters per second square. Now similarly, in the second part of the question, you understood now, here we are doing vector sum of two forces which are perpendicular to each other. Theta is 90 degrees and the magnitude of each is F naught. So it just becomes root of F1 square plus F2 square, which becomes root 2 F naught. Now, similarly, in the second part of the question, you are applying on that horizontal surface, on that block. Now you are applying one force of 2 F naught, right? And another force of F naught at an angle of 45 degrees to it. If you take the vertically, if you take the view from vertically above, this is the combination of forces which is acting on the block. You see the block from above. The combination of forces acting are this force of magnitude 2 F naught, but direction like this. Let's say this is F1 and at an angle 45 degrees to it. So let's say you're taking this as your y-axis. This is your x-axis. So in this diagram, this is your x-axis. Yeah, students, I just had an internet dropout. Lost connection momentarily. Just reconnecting. Just give me a second. Right. So, so your net force, you can see here, will be in this sort of direction, like this. So you can just use the statement of triangle law here. Magnitude of F1 is 2F0. Magnitude of F2 is F0, and the angle between them is 45 degrees. So the magnitude of the net force will become square root of this F1 square plus F2 square plus 2 times F1 F2 cos theta. Okay, so this will become your net forces magnitude. So the acceleration in this case will be, the magnitude of acceleration will be net force divided by mass. So that will become F naught by m into square root of 5 plus 2 root 2. Okay. So now substitute from equation 1, F naught by m was equal to 5 meters per second square. So in this case now the acceleration becomes 5 into square root of 5 plus 2 root 2, for which you will do an approximate calculation. So that is approximately 5 into square root of 5 plus 2 into 1.4. 5 into square root of, this is 2.8, so this will become 7.8. So when you work this out, this will come out approximately 13.96 or 14 meters per second. Okay. So actually you can leave the answer here, it's fine. In this particular worksheet, I have given you a more detailed calculation in the answer key. This is as good as this. Okay, so I'll just leave this third part, or rather the second part, for you to see in a little more detail. Anyway, so hope this is clear. Okay, Pritesh, don't worry. All right, so this is the second question. Now, I got logged out, so I missed out on the messages. So please send me the doubts you have once again, please, if you don't mind. I think third question, all of you were good with. Yeah, thank you. So next we'll move on to the 7th question. Okay, if anybody has a doubt before question 7, please send me a message. Okay, I'm moving on to question number 7. If anybody has a doubt in a question before 7, question 5, okay. All right. We will move on to question 5 then. So we'll go in this order: 5, 7, 8, 9, 11, 12, 13, and 15. Okay. So turn to question number 5. All right. So in this, what is happening is that you are pulling an object along a horizontal surface, but in order to make it move with constant velocity also, you are having to apply some force. Okay. So even when this is moving with zero acceleration, with constant velocity, is situation maybe we are seeing that we are having to apply some force on it. In fact, that force is 300 Newton. Okay. So if the acceleration is zero, that means there is some drag force. Okay. Acceleration is zero in this situation. It means that because velocity is uniform given to us, so it means that in this case the net force is zero. Okay, even though F is equal to 300 Newton is being applied. So that means that there is some friction, okay, or what they are calling as a drag force. It's dragging it back. Let's say that is denoted by the symbol small f, which is usually the symbol we use for friction. So that is acting backwards like this. Okay. So now you see the net force is zero, means in this particular case, capital F minus friction is zero when F is 300 newtons. So that means that the amount of friction that is acting on the body, or the drag force, has a magnitude of 300 newtons. This is your so-called drag force or friction. So now on the same body, in the second case, we increase the amount of external force that we are applying. We increase it to 500 newtons. So now we are bumping up the force to a value, let's say F prime, which is 500 newtons. So we'll see that this starts accelerating now, because the amount of friction acting will not change. That will remain the same. Okay. That friction will be equal to 300 newtons only. Okay. But F prime is now increased to 500 newtons, and the mass of the body is given to us 100 kg. So we'll see that this time the net force is becoming 500 minus 300, becoming F prime minus friction. So 200 newtons is the net force and the mass is 100 kg. So you can see that the acceleration has bumped up to 2 meters per second. So we are not making any, judgment about friction, that it depends on mass, it depends on coefficient of friction and things like that. We'll come to those things later. We're just using the data of the question to understand how much the drag force is. And from that, when we increase the external force from 300 to 500, the drag force remains 300. Okay. So hope this question is clear to people. Anushka, Rakshit, hope the question is clear. Okay. Let's move on to the 7th question next. So 7th question is a bit of a calculation heavy type of question. So the background to this question is that acceleration due to gravity g is actually not a constant quantity. It varies with height above the surface of the earth. And this is just showing you that variation. So in question 7, is given to us the variation of g, that is the acceleration due to gravity, okay, in the Earth's gravitational field. So variation of the value of g with height h from the Earth's surface. Okay. So this is part of a larger principle of Newton's law of gravitation, which we'll be studying in a lot of detail in a later chapter. But here let us try and understand like this, the way the question is explaining it actually. So if this is the Earth, and we are at a position, okay, I'll explain the relationship between dyne and Newton, okay, don't worry. Are you clear? So this is the center of the Earth, and this is the radius of the Earth, and now we are at a position which is at a height further h above the surface of the Earth. It doesn't matter whether we are here or we are here, but as long as the height is like this, then the value of g will experience over here. This will be different to the value of g that is experienced on the surface of the Earth. On the surface of the Earth, so at different heights, we'll experience different kinds of, so suppose this is a height h1. So at this height, an object which is dropped will experience a different acceleration due to that. Like this. So this variation of the value of g with the height above the surface. This is given to us in the question. So this variation is given to us by this formula, that g at a height h is equal to g at a height of 0 multiplied by this factor. Where RE is the radius of the Earth, which is given as 6370 kilometers. So that is the data given to us in this 7th question. And we will take G0 G0 on the surface. Yeah, sorry, this whole square in the denominator. My mistake. The given expression is like this. Okay. So this is anyway, this is given in the question. This expression is given. Okay, so now first part we have to find the weight of an 80 kg man, okay, in newtons and in pounds on the Earth's surface. So I'll give you the relationship between all the units. Now units of force. The SI unit is the one we typically use. Is Newton, okay, where 1 Newton equals to 1 kilogram meters per second square. It's coming from F is equal to MA. Second unit you should know is the CGS unit, okay, which is called dyne. So CGS, as you know, stands for centimeter gram second. So in CGS system we define length in centimeters, we define mass in grams, and we define time in seconds. So 1 dyne becomes 1 gram centimeter per second square. So we can also express 1 dyne as these many kilograms into these many centimeters per second square. So 1 dyne becomes 10 raised power minus 5 kilogram meter per second square, or 10 raised power minus 5 newtons. So this is the relationship between newtons or dyne and dynes. So we can say that 1 Newton of force is equivalent to 10 raised power 5 dynes of force. What? No, correct. In this thing, mass is in grams and length is in centimeters in CGS unit. So that is why 1 Newton is 10 raised power 5 dynes. Oh, this. Correct. Okay. Yes, correct. Alright, so this is converted this way. Okay. And there is also this is an outdated system, not used anymore. This is foot pound second system. So this is the unit of mass. Okay. So 1 pound so you should remember the unit that 10 pounds is equivalent to 4.5 kg. Okay, 10 pounds are equivalent to, or in other words, 1 kilogram is equal to 100 by 45 or 20 by Newton pounds, or alternately 1 pound is equivalent to okay. So something that has a mass of 1 kilogram will have a weight of these many pounds. So this is first of all the relationship between the units here. And we'll come back to the question just a moment. But you should remember this. And you should remember this. So now coming to the first part of the question, you want to find the weight of an 80 kilogram person on the Earth's surface. Okay. So the weight will become mg, where here g will be g on the Earth's surface. Okay. So the weight will become 80 multiplied by 9.8, this much in newtons. Okay. So that's 98 into 8. That's 800 minus 16, or 784 newtons. Now the other thing is that we say that 1 pound weight is equal to basically a mass of 1 pound multiplied by 9.8, or so 1 pound, if we express in weight, it means so many newtons. Okay, so therefore this weight of 80 kg multiplied by 9.8 in pounds, it is equivalent to okay. So in pounds, he will weigh on the Earth's surface this much. Okay. So the weight of the person in pounds will be expressed this much. Oh, the range is, I'll explain. It tends to infinity actually, because for g to become 0, the denominator has to tend to infinity. I'll explain, Ayush. Okay, so this is the first part. Now in the second part, we have to find weight of the man in newtons at a height of 300 kilometers above the Earth's surface. Okay, and what is the mass of the person at that height? So what we have to understand is mass is independent of height. Okay, it is the weight which is varying because acceleration due to gravity is varying. So at a height of h equal to 300 kilometers, okay, g will become this quantity. So that will become 9.8 into become this whole thing in meters per second square. So I'll just do an approximate calculation of this. So this will become 6370 divided by 6670, and you whole square that and multiply that with 9.8. So this will come approximately equal to 8.94 meters per second square. ये आ जाएगा g का वैल्यू. So now what will happen is, therefore at this height, the person will have a weight of this much now. You will have a weight of 80 kg multiplied by g at that height of 300 kilometers. Okay, so his weight would have decreased to about 715 newtons. Whereas on the surface of the earth, you could see that the weight was 784 newtons. So it has gone down from 784 to this much. Okay, but keep in mind here that the mass is independent of height. So this is independent of height above the earth. If he goes to outer space also, where g is tending to 0 from the earth's surface, no, Snikita, you can't do these calculations that fast actually. I mean, this is a question for your knowledge purpose. You will not get these type of calculations in exam, don't worry. In exam, you will get easier type of calculations. So if this was a question in JEE type of thing, you would have got the value of radius of the earth as a more approximate thing like 6400 kilometers. Okay, and that height instead of an odd value like this might have been given as something more easy to handle, like suppose it is given as 800 kilometers. Then you can see that that RE upon RE plus H whole square is easier to handle. This would have become, so because this 1/8, this would have become, this denominator would have become 1 plus 1 by 8. So that is 9 by 8. So this would have been 8 by 9 square. So it would have been easier to calculate. And g would have been taken as 10. So this would have been something like this. So this kind of calculation you will get at your JE level or your NEET level. You will not get something which is so difficult to calculate. Now, Ayush, coming to your question, okay. So you can see here that in this expression, g at a height h is 9.8 into radius of the earth upon radius of the earth plus height, iska whole square. So you can see here that this g will tend to 0 as h tends to infinity. So practically that basically what means is that when the height is very large compared to the radius of the earth. Okay. So given that radius of the earth is about 6370 kilometers. Okay. So for example, if we take the height equal to the radius, then your g will become 9.8 into 1 by 4, you can see, because this factor will become 1 upon 1 plus 1 whole square, so that will become 1 by 4. So it will become 1/4 of acceleration due to gravity on the surface. If we take the height as, let's say, 3r, so g at that height will become 9.8 upon 3 plus 1, 4 square, so that will become 16. So this will become 1 upon 1 plus 3 square. You can see how rapidly it's decreasing. Now like that, suppose you take a height of, let's say, 1000 times the radius of the earth. So g will become how much? It will become 9.8 into 1 upon 1001 whole square. So it will become, approximately 9.8 into 10 raised power minus 6. So you can see it's become very negligible. Why it's become negligible? So it's almost tending to 0 because this height is now very, very large compared to the radius of the earth. Okay, understood the concept now. So as the height increases, the acceleration due to gravity decreases, but as the height becomes many orders of magnitude more than r, so in this case 10 raised power 3 times r, then your acceleration due to gravity becomes a negligible quantity. Okay, so more about, we'll discuss this in the chapter on gravitation. We will see that this formula actually comes from a more precise formula, which is to do with the gravitational force between a spherical body and a mass. Okay. But anyway, this is this question till now. Now moving on to the 8th question. Okay. Now 8th is a question which I wanted to discuss in particular because it will give us clarity about a lot of things about the application of Newton's laws. So question 8, let us understand it in detail. So you have this body which is of mass 2 kilograms, I think, yeah, given to us. Okay. And alongside it you have another body so right alongside it you have the other body of mass 1 kilogram. Okay. This combination is kept on a frictionless horizontal surface. So this is and now what is happening is some external agent is applying a force on the 1 kg block but pushing it by application of a force of 5 newtons. So we want to find the contact force between the two blocks and the acceleration and all that. Okay. So first of all, let's understand what forces act on each block, okay, in this system here. What all forces are acting? So if you consider here, the block M1, it has what all forces acting on it? It has its weight. Now the ground is pushing it upwards with an equal and opposite force, which is the normal reaction that the ground is applying. But because we are applying this force F, it's also getting pushed back by this block it is against with some normal contact force N. Okay. So here this is the normal contact force on M1 applied by M2. And similarly, if you see the situation of M2 next, so if you see the situation of this block, what all forces are acting on it? You have its weight acting, you have the ground pushing it up with a normal force. And this block, because you are pushing it with F, it's pushing against this with normal force. So this has the same magnitude as this, okay, but this time this is the normal reaction or contact force on M2 applied by M1. So this and this are an action-reaction pair. Okay. And of course, weight and normal reaction applied by the ground. Okay. And this whole system has some acceleration in it. So when you apply Newton's second law, net force is equal to mass into acceleration. Okay. Now apply this to body M1. So in M1, what is happening? The forces acting are a combination of all this: weight, normal reaction, this force F, and this normal reaction N. Okay. And under the action of these forces, you can see that it's accelerating along this direction. So what is happening? M1G is balanced by the normal reaction the ground is applying. No, Dhruv, how can normal reaction cancel here? We are applying Newton's law to which body? To M1, na? So action and reaction, दोनों M1 पे act कर रहा है क्या? Can both action and reaction act on the same body? No, na? So that's how. So how they can cancel? So that's why I'm saying, na, concentrate on this thing. You are applying Newton's second law to which body? Body M1. So only this N acting backwards is acting on it now. So F minus N becomes the net force. This is the net horizontal force. And that should be equal to mass into acceleration. Okay. So 5 newtons minus N is equal to 2E. This becomes our first equation. And now secondly, apply Newton's second law to the block M2. Now on the block M2, you can see that there is N acting like this. Normal reaction that the ground is applying like this. Its weight is like this. And again, it is accelerating like this. So again, N2 balances the weight. So there is no vertical acceleration. Okay. But the net horizontal force comes N is equal to 1 kg. That becomes our second equation. And now all you have to do is solve these two equations. Next up, all you have to do is solve these two equations. Okay. Or F minus N is M1A and N is equal to M2A. So if you just add these two equations, you have F is equal to M1 plus M2A, or acceleration is equal to F upon M1 plus M2, which here will become 5 by 3 meters per second square. And then substitute this back in second equation. So 1 kg into 5 by 3 meters per second square. So the normal reaction becomes 5 by 3 or approximately meters. So this is the proper way of solving this question, by using systematically Newton's second law to each of the bodies in the system. No, that is if we apply the force and it is balanced by friction. We can always apply a force which is more than the amount of friction. And that is when the body will move. Okay. So if the body is at rest, okay, if the body is at rest and let's say the friction acting on it can be up to 5 newtons. So to make it move, we'll have to apply a force of more than 5 newtons. Okay. So we'll have to apply a force initially of more than 5 newtons. Now once it starts moving and is gained some velocity by then, if we reduce the force from the initial value to 5 newtons now the acceleration being 0, it will continue to move at the constant velocity. Okay, but to bring it to the state of constant velocity, you will have to apply some force initially, which is more than the amount of maximum friction. Okay, so hope this 8th question is clear to all of you. Okay, now moving on. Ninth, 11th, 12th. So 9th question is again about vector addition. You can see that on that 10 kg block, in the horizontal plane, on a smooth horizontal surface, you are applying two forces like this. This angle is 30 degrees. This force is 20 newtons in magnitude, and this force is also 20 newtons. So your net force will be in some direction like this, the triangle law. So you can see that now you can use the rhombus principle here. When you draw this vector parallelogram, you see that it's actually a rhombus. No? So you can use that trick because this side is equal to this side. And this angle is 120 degrees. So when you complete this parallelogram, it's actually a rhombus. So the vectors sum. This will be the resultant of F1 plus F2, or what we call the net force here. Now you can use the trick here that in a rhombus, what happens is that if these two sides are A each, and this total angle is theta, okay, then what happens is that it bisects this angle. So this angle is equal to this angle, that is theta by 2. Okay. This also bisects. So this diagonal, now this one, this becomes how much? It becomes 2a cos theta by 2. So you can use this over here. So here the magnitude of net force will become 2 into 20, which is 20 root 3. Basically, you know that if magnitude of A is equal to magnitude of B, okay, an angle between them is theta, then, sorry, it's half, my mistake. We'll come back to that, okay. That actually becomes 2a cos theta by 2. Okay. So you can use this theorem. Okay. And the resultant equal to A plus B is at alpha equal to theta by 2 with respect to T. So this is that rhombus thing. Okay. Yeah, coming back here, this is half, so this will become 20. It will become 20 newtons. So the acceleration will become 2 meters per second square. और वो जो acceleration का direction होगा, it will be along this sort of direction. This will be the direction where this angle and this angle will be 60 degrees. So hope this is clear. So this is just that little theorem from vector algebra. When this situation happens, that mod A is equal to mod B, okay, the vector parallelogram becomes a rhombus. So that rhombus has these properties. Just to recall that for a moment, because it's quite important when it comes to applications. So the rhombus has this important properties that important properties that the diagonals bisect each other perpendicularly and also bisect the angles. So if this side has the same magnitude as this side, let's say small a or capital A or whatever, and this whole angle is theta, then the primary diagonal, which is the sum vector, bisects this angle. And the secondary diagonal, which is the difference of the two vectors, becomes a perpendicular bisector of the primary diagonal. So this angle becomes 90, and also this becomes equal to this. This becomes equal to this. This angle becomes equal to this angle. And this angle becomes equal to this angle. Okay. So the diagonals rhombus perpendicularly bisect each other. Okay. And also are angular bisectors of the sides. Okay. So alpha becomes theta by 2, beta becomes 90 minus theta by 2, and the diagonals become like this. So this is the rhombus properties, or the properties when special case of vector addition, vector subtraction, etc. So this is just a quick recap of that concept. You've seen this in vector algebra, but this kind of thing comes in very handy in a small application like this. So the moment in this diagram you saw that the two forces were equal in magnitude and the angle between them was 120, you would have realized that the net force was becoming 2 times F into cos of 60, like that. So just do a recap of this and write this down if required as a side note, okay? And then we will come to the question number 10. Right, so now moving on to question number 10. Tell me vector addition करना बेटा. There's nothing else in it. So the forces are just given in I cap. So mass of the object is given to us as 4 kg. And the two forces acting on the body are 2 I cap minus 3 j cap. And second force equal to 4 I cap plus 11 j cap, both in newtons. Also newtons, this is also newtons. So the net force you just find out by adding these two. So the net force is becoming 2 plus 4, so that's 6 I cap. Okay. And then minus 3 plus 11, so that is 8 j cap in newtons. So the acceleration of the body will become net force divided by mass. So that is 6 I cap plus 8 j cap divided by 4 in meters per second square. So the acceleration as a vector quantity becomes 3 by 2 I cap plus 2 j cap in meters per second square. And therefore the magnitude of the acceleration becomes that will be 5 by 2 or 2.5 meters per second square. So this is the solution of the 10th question. So it's starting from rest. U is equal to 0 at t equal to 0. Therefore, V will be equal to acceleration into time, and S will be equal to half a t square. Okay. So V will be equal to 3 by 2 t I cap plus 2 t j cap, and the displacement will become 3 by 4 t square I cap plus t square j cap. Now just substitute the value of time in seconds, and you will get the displacement in meters and the velocity in meters per second. Alright, so hope this application is clear. The last part is kinematics, because the acceleration is uniform, so I'm just using that relation that V is equal to U plus AT, but U is also 0, and S becomes half AT square. Okay. So that's the 10th question. Hope that is clear. Yeah. Now moving on to the 11th question, it's just application of differentiation. So in question 11, what is it? I think momentum is given, right? Velocity of the body is given along a straight line. This is the velocity and the mass of the body is m. So we have to calculate the momentum at the instant when the force is zero, isn't it? What will be the momentum of the body at an instant when the force becomes zero? So momentum in general is m into v in scalar notation here. So that is m v naught t into 12 minus t square, or that's the same thing as this. Now the net force is this. So it is differentiation of this term with respect to time. So the net force will become mv naught into 12t minus differentiation of t cube. So mv naught into 12 minus 3t square. Okay, so that is your net force. So therefore, net force is equal to 0 when mv naught into 12 minus 3t square is 0. So that means 3t square minus 12 should be 0. So further, that gives you two solutions, but time cannot be negative, so we'll take only the positive solution here. So t equal to 2 seconds or t equal to minus 2 seconds, which we'll reject as a solution. So you can see that net force is becoming 0 at t equal to 2 seconds. Okay, and at that point of time, the momentum is equal to that value. When the momentum is 16 m. Alright, so as I said, nothing but an exercise in calculus, differentiation principles. That is what question 11 is. 12 is also much the same. Okay. So 12 also do in the same manner. X is given as a function of time. So velocity is dx by dt. So acceleration is second derivative, or dv by dt. Okay, so 12th question. For those of you who asked, is very simple. It's displacement or position, whatever, x as a function of time in one-dimensional motion. It's moving along the x-axis is given to you as a function of time. Some kind of power 4 function. alpha t to the power 4 minus beta t cube, where alpha beta are constants. T is time. Okay. So its velocity along the x-axis will become dx by dt. So differentiate this. So that is 4 alpha t cube minus the beta t square or t cube. This beta t cube. Okay. So this will become 3 beta t square. Okay. And acceleration, which is dv by dt, will now become differentiation of this term. So that will become 12 alpha t square minus 6 beta t. So you can see that from this you know the force is equal to mass into acceleration. From this you know the momentum is equal to m into v. So now just that thing you have to do, that in the first part you have to find out velocity is equal to 0 at what time, and then find out the force at that time. And the second part you have to find out that the force is equal to 0 at what time, and then at that time find out what the velocity is. Okay, so can you finish this question yourself, people? That's the 12th question. Okay, good. Right. Now let me explain the 13th question. Okay, good, ask me. So in the 13th question, you have the concept of the bullet being fired by a gun and coming out of the nozzle, or what is called the muzzle of the gun, the pipe or the muzzle or the barrel of the gun also it's called. So suppose I'm just making the diagram of the muzzle of the gun, not the rest of the gun, or what we also sometimes call as the barrel of the gun. So the rest of the gun is here. So this is the barrel, or what is more precisely called the muzzle of the gun. Okay. So this has a length L. Now as the bullet comes out from this side, it has a final velocity of v. Okay. So a bullet of mass m. But when it starts at the back of the muzzle, when it starts its journey, where basically it is hit by the piston of the gun, okay, and there's a fast combustion reaction which causes it to get propelled forward, we'll assume its initial velocity is 0. Okay. So what is happening is that it is covering a displacement of L, and its velocity is changing from 0 to whatever this final v is. Okay, let's say this is v0. So it has an average acceleration which is just a second, my software is hanging. So it has an average acceleration which is v0 square by 2l. We use this equation. We use this equation that v square is equal to u square plus 2as, where this is either the uniform or average acceleration, and s is equal to l and u is 0. Okay. So the average force will become mass into average acceleration. Just use this. Okay, understood the concept now. So you are using a concept from kinematics actually, that even if this variable acceleration, the average acceleration can be calculated by using this equation. That is the 13th question. So this will become 500 squared divided by 1. You can see it's a huge amount of acceleration. It is 25 into 10 raised power 4 is the average acceleration. So that into 0.05 kg will be quite a significant amount of force, the average force generated by the system. This in this question, this will become 500 squared divided by 1. So further, this thing here will become 0.05 kg multiplied by this, which is 2.5 into 10 raised power 4. This kind of value you will get in newtons as the average force. Alright, so let's come to the last question, the 15th one. 15th is again about the I cap J cap notation. Okay, so similar kind of problem as the one we saw before. The two forces are given in I cap J cap. You have to express the acceleration, velocity in unit vector notation after 5 seconds. Okay. So same like you did in question 11. No? Sorry, in question 10. Similar thing you do over here. Find F1 plus F2 first by vector notation. Okay. Is given F2 is given. So you have find net force in I cap J cap notation. Then divide the net force by mass. Find the acceleration. Again, this acceleration will come out to be some x component and some y component. So that is your acceleration in I cap J cap notation. Okay, whatever this comes out to be. Now your initial velocity is 0. So velocity at time t will just become acceleration into t. So in component form, this will become Vx I cap plus Vy J cap. On the other side will become Ex into T I cap plus Ey into T J cap. And your displacement will become half at square. So in component form, your displacement will have some x component and some y component. This will be x I cap plus y j cap. That will become half ex t square I cap. So all you have to do here is substitute this acceleration in component form here and whatever values you are getting. Right, so you people can finish this question. Right. Just give me a second, guys. I have to reload the whiteboard software. It's getting hung. Just give me a minute. Right. So that completes the discussion of the assignment. Now we will move ahead by understanding some more about the forces and things like that in Newton's second law. Just give me a minute. I'll start the whiteboard software. So with this worksheet 1, what we saw is some basic examples of the applications of Newton's second law, and in the process we also saw action reaction principle and all that, but primarily we saw it applied to individual bodies where only some external force like a pushing force or a pulling force or things like that are applied by somebody on the body. But now gradually we'll move on to systems where there are more types of forces involved, so we want to gradually understand more about types of forces, etc. So first of all, in Newton's second law, we have seen the effect of force, that net force is equal to rate of change of momentum. But what actually is force? That is not something that is explored so much in detail by Newton's second law. So we have to understand a little bit more about force, the nature of force. Okay. What is basically a force? So if you think about it, think of all the examples we did so far in this question, etc. In these questions, etc. You'll understand that force is an interaction, okay, between two bodies or two particles, okay, or two systems. Okay. For example, when we talk about gravity, it is an interaction between masses of bodies. I'll come to this in more detail, but I'm just giving you an example. Okay. For example, when we talk about elasticity as a force or elastic force. Okay. So what is that? So for example, you have two bodies attached by a spring. All of you seen a spring, how it looks. Okay. Now suppose the spring is extended, so we pull the bodies like this so that the spring gets stretched. So this is, it's in a stretched state now, the spring. So what happens is it applies, so within this system now, it applies an elastic force like this on these bodies. So these become elastic force, okay, acting due to the spring's stretched state, okay, within this system. Okay. Then another example would be, if we have a positively charged body and another positively charged body having charges plus q1 and plus q1, okay, at rest initially, they would apply repulsion force. So this would be an example of what we call electrostatic repulsion force. So this force comes due to the nature of charge, which is a fundamental property that acts in bodies. Okay. Or another example would be, if you bring two magnets, they would tend to repel each other. So this would be magnetic repulsion force. So again, this comes from the magnetic field created by the magnets. These are two bar magnets. And so on and so forth. There are so many different types of forces. But everywhere you can see what is the force really. It is a type of interaction between either two bodies or two particles or interaction within a system. So at a fundamental level, what is a force? It is an interaction between two things. Okay. Elastic force is equivalent to Ayush. Just a second, I'll just go through your doubt. Nikita, don't worry. These are not things you need to write down in detail. I'll be providing you with the notes anyway. I'll give you time to write down the significant part. Okay. So, yeah, I mean, Ayush will come to that, whether it's a distributed force or the overall, the spring has the property of elasticity. How that elasticity is acting on this body, let's say M1, is that it's creating an elastic force towards the right hand side. How it is acting on M2 is it's creating an elastic force on M2 towards the left hand side. Okay, and things like that we'll see. Okay. However, the interesting thing is that of all these different type of forces that we can talk about and discuss, etc. Okay. There are, so we just understood that force is interaction. Okay. So that means force is something very fundamental. It comes from the nature of different systems, or the nature of physics itself. That why bodies tend to interact with each other. That is the very fundamental nature of physics. It's the very fundamental nature of how the principles of physics work in different aspects of the universe, or different aspects of the physical universe around us. Okay. So in that, it's very interesting to note something that we were discussing in the very first lecture that I took for you people, where we were exploring what the scope of physics is about. We understood that in physics, in all of physics that we know, of course, till date, because there's always a possibility that there'll be something that we don't know about and it will come up in some experiment or some principle later. Okay, so till date, whatever we know in physics, okay, there are 4 types of what we call fundamental forces. And everything else is a combination of these 4 fundamental forces. Okay. Gravitation, which is due to attractive property of mass, okay, or because mass attracts mass due to this property of gravitation. Then second is the electromagnetic forces, or the electromagnetic interaction. This comes because of charge. So at a later stage, we'll understand in more detail that electrostatic force, therefore charges at rest, okay, or static charges, and magnetic forces act when charges are in motion. That is why electric current creates magnetic field. Okay. Then the third type of force is the strong forces, or these are also called nuclear forces. So these are the nuclear binding forces which keep nucleus of an atom intact. Okay. Yeah, Dhruv, I told you don't need to write down what you've written, what I've written above. I will give you time to write down what is significant in this. Okay, that was for your understanding. You can take it down from the notes later also. Please pay attention to what I'm saying over here. That is more important. And the fourth type of force is the weak forces, okay, which are the forces or interaction between subnuclear particles. So of all the forces and all the types of interactions, some of whose examples I give you above, the fundamental types of interaction known in physics are only four. Okay, so this is something that we are going to understand in more detail as we go along. Okay, and in this also you will see that for us, most of the forces that we see in our everyday life around us, so-called mechanical forces, they come as a result of these two properties. We don't really see the effects of nuclear forces or the weak forces in our everyday lives around us unless we experience the force of an atom bomb or something like that, or we are dealing with particles physics experiments in those kind of cyclotrons, etc. In our everyday situation, we are never influenced by those kind of strong or weak interactions too much. Our everyday experience is limited to gravitational and electromagnetic forces. So you can take down this part here. Leave out the part before. They are just examples for you to understand as you read the notes later. So at a fundamental particle to particle level, there are only these four types of interactions which are known. So in fact, these two are not as well understood in physics as these two. Okay, there are still areas where research is showing us new things about these forces every day. They're not fully understood in that sense. Whereas gravitation and electromagnetic interactions are very well described by the laws of physics, or very well understood by us through the laws of physics. Yeah, the strongest type of interaction among this is the strong interaction, the strong forces. That is why the name is like this actually, because this is huge amount of force within the size of the nucleus. That is why the energy related to strong force is extremely high, and that is why those atomic processes or nuclear energy is the most efficient form of generating energy. Okay. Now let's talk about each of these. Okay, so for example, when we talk about in our everyday lives, okay, some common forces. So when we talk about gravitation, yeah, weak forces are the forces between subnuclear particles, Nikita. Like when protons and neutrons are broken down into quarks and leptons and fermions, the type of interaction that happens between them at the subnuclear level, those are called the weak forces or electroweak forces. And very little is understood about them. It's still an area of research in physics. So, for example, you would have heard of these, high energy physics experiments, like the particle physics experiments where particles are smashed against each other at very high velocity, going through those, tunnel kind of experiments, which are called the cyclotron experiments or particle accelerator experiments. And as they smash against each other, the interaction is understood between them. So those type of interactions are the weak interactions. Okay, so they are an area of research in physics. So that's why we will not get into too much about weak forces and the nuclear forces over here. However, gravitational and electromagnetic forces are very much part of our 10+2 syllabus, and we'll be studying them in more detail. But again, coming back to everyday life in the world around us, gravitational forces example. Yes. See, the first example is weight of an object or body on the Earth's surface. Okay. So this that we know mg, which always acts vertically downwards. But this is fundamentally basically what? This weight of an object, it is nothing but the gravitational pull or attraction experienced by a body of mass m, okay, towards the Earth's center, okay, due to the Earth's mass. That is what it is actually. Okay. So wherever you're present on the Earth's surface, wherever the body is present on the Earth's surface, if this is the center of the Earth, then the gravitational pull or the gravitational force will always be a vector that is acting on whatever body directed towards the Earth's center. So that's why it becomes a it becomes a vertical surface, because this becomes a horizontal plane. So this direction becomes vertically downwards. So that object is here, it will experience gravitational force like this. That object is here, it will experience. So that is why for a person standing on the surface of the Earth, over here, for a person standing here, it appears to be vertically downwards, because in your frame this is the horizontal plane. If you're standing over here on the surface of the Earth, you see this tangent as your horizontal plane. So you see the gravitational force like this. And G has a constant value of 9.8 or approximately 10 meters per second. But if you think about it, this is not the only gravitational force that you experience in your lives. Okay. This is the most predominant one because the Earth's mass, the mass of the Earth is huge. It's much, much larger than any other object. So that is why mg dominates a lot. Okay. So at a later stage, we'll also learn that the reason why the value of small g, acceleration due to gravity, is uniform everywhere on the surface of the Earth is because the Earth is more or less a perfect sphere. If the Earth had been some other shape, then g would not have been uniform on its surface. And in fact, because the Earth is actually slightly flattened at the poles, there is a slight variation in acceleration due to gravity between the equator and the poles. But that variation is very negligible. So for our purpose of mechanics problems, we take g to be uniform everywhere on the surface of the Earth. Alright. However, in our everyday lives, we do see the effect of gravity in other things. For example, we see tidal waves which are affected by the gravitational field of the moon. We see comets, we observe comets once in every few years or few decades, and comets' path or trajectory is because of the gravitational forces between planets and comets or stars and comets. We are constantly experiencing the solar cycle where the Earth is moving around the sun in a type of an orbit where the distance keeps changing from season to season. So that is the motion of the Earth around the sun in a bound orbit is also as a result of the gravitational pull that the Earth experiences because of the sun. So these are all systems, or these are all phenomena which are driven by gravity. Any orbital motion of celestial bodies, whether it is a moon around a planet or its planet around stars, or the way star systems or solar systems are moving about within a galaxy. So all these phenomena in the universe, the fundamental driving force behind them is nothing but the gravitational attraction. Yes, so in fact, every mass has gravitational force, beta. So even your pen is applying some gravitational force on you, but that force is negligible. It's very, very small. If you calculated it, its order of magnitude would probably be something like 10 raised power minus 50 or 10 raised power minus 60 times the weight of the pen. Okay, because your mass is that much less compared to the mass of the Earth. So that is why when you drop the pen, it goes straight down. It doesn't come towards your body. But suppose this pen and you were both in outer space where there's no Earth, then the moment you release the pen, it would come towards your body because your body's gravitational pull would become the predominant force on it. Okay, so more about gravitation in a chapter called Gravitation later. Now, next we will see some second category of common forces, which are contact forces. So, like earlier we saw today, now if this body is moving like this, there are two types of contact forces that would be acting on this. One is a normal force, normal reaction type of contact force, okay. And the other would be a friction type of force. Now, fundamentally, contact forces are because of what? Are they gravitational forces? No. They are interaction between molecules now. So they are as a result of the electrostatic interaction between the molecules, atoms at the surfaces of contact. See, anything to do with intermolecular force or intermolecular attraction or intermolecular repulsion or atomic interaction or molecular interaction is to do with charge. Okay, whether you're talking about bond forces or you're talking about elasticity forces or you're talking about repulsion forces, they are all to do with the nature of charge of molecules and atoms. The fact that atoms and molecules consist of charged particles, that is why they interact with each other when they come in contact. So for example, you keep this block, suppose this is a metal block, on a liquid surface, you will see that it starts sinking. Okay, why? Because the interaction between the liquid molecules and the solid molecules here are different compared to the interaction between, let's say, a wooden table surface and that block over here. Okay, why the wooden surface molecules don't separate as they are pushed by the weight of this object? Okay, because they have a stronger rigidity. Okay, they are rigidly attached to each other. So why they are rigidly attached to each other? That is again because of the intermolecular bond. And again, where is the intermolecular bond coming from? It is coming from the charged particles that the molecules and atoms consist of. So any type of contact forces at the fundamental level, they are which type of interaction? They are electrostatic interaction. So whether you talk about friction or normal reaction, it is the interaction. So contact forces are interactions between molecules of materials. So that is why at a fundamental level, they are which type of forces? Wood doesn't sink in water because wood has a lower density. So water applies a force called, so because of the pressure force that the water applies from below exceeding the weight, okay, wood doesn't sink completely and it's only partially submerged and it's floating in water. So again, where does the force due to pressure come from? It's because the water molecules are pressing against the wood molecules, okay, and applying a sort of interactive force. So again, that is coming because of the nature of intermolecular interaction, and that is nothing but electrostatic in nature. It is not because of nuclear forces. It is not because of gravitational interaction. It is not because of the electroweak interaction between the subnuclear particles, but it is only because of the electrostatic interaction between the charged particles that are the constituents of matter or the constituents of molecules and atoms. Okay, understood this? Now, the final thing that we'll add to our discussion today. Oh, you have a class at 10:20. Just give me a couple of minutes, okay? I'll wind up just a couple of minutes. The final type of force that we'll wind up with today is a force called tension, or it's called tensile force. So this is the type of force. It's a type of internal force that develops along the length of a rope or a string or a chain when it is given a tendency to stretch. Okay, due to external forces. So, for example, on a surface, you have just a chain like this. Okay, so it is loose right now. So it has no tension. Okay. But next up, what you do is on the chain, you're applying two equal and opposite forces from this side. It's on the horizontal surface, so its weight is balanced by this. So now you see that the chain is tense, okay, or it has a tension force along. Okay. So what is that force actually? So if you think about this last link of the chain, it has an external force on this side, but some force with which this link is pulling on this. So if this is the first link and this is the second link, this is the force on this. Okay. Now think of the second link over here. It is being pulled with an equal and opposite force on this side by the first link and is pulling against the third link. Okay. And like this continues till you come to the last link on this side. So every link of the chain is interacting with every other link, okay, with some tension, and that tension P is equal to F, is uniform everywhere in the chain. So again, this tension T is what type of force at the fundamental level? Okay. This tension T, it is again electrostatic interaction between molecules. So since you guys have a class coming up in 5 minutes or so, I'll wind up here. But just the last point over here. So instead of the chain, if you have a string or a rope, you'll see the same situation occurs over here. Suppose you have a string, but now you're pulling this system with some force. So the moment you're pulling it, the chain or the rope here, or the string in this case, it has a tendency to get pulled. Okay. So what is happening here is this block M2 is experiencing a tension force because of this rope like this. Okay. And this block M1 is getting pulled like this. So this has an acceleration A. This has the same acceleration A. And you can see that over here, this is an action-reaction pair. This is an action-reaction pair. Okay, so we will continue from this point onwards in the next lecture. Okay, so in the meantime, you can also read a little bit in the theory notes from your module or from Resnick Halliday, etc. more about tensile forces and tension and how they act when we give a tendency for stretching for a rope or a string or something like this over here. But again, the important point here is that you understand at the fundamental molecular level or at the particle level, this force of tension is also coming from which type of interaction? It is coming from molecule-molecule interaction. So that is nothing but electrostatic interaction in nature. Okay. So we'll conclude here today. Yeah, I'll scroll up. I'll send you the notes, don't worry. Okay. So tension is the third type of mechanical force we're discussing about. Okay. No, solid body has more electrostatic interaction beta because the intermolecular bonds are stronger, na Ayush? That is what is giving the solid its rigidity. In liquids and gases, the molecules are more free, so the intermolecular bonds are weaker. Okay, so that's it today, people.